population is in equilibrium, then its population structure can be calculated with the binomial. So the binomial implies stability. As long as big A and little a do not change, the population structure will never change. But again, on Friday, we went through and listed briefly 4 different mechanisms that change allele frequency. And so a mechanism that changes allele frequency will change the population structure. As big A allele frequency goes up or down, the population structure will change. And so what we're going to do now is take a more thorough look at these mechanisms and see how they change allele frequency and how that alters the population structure. So the 4 things that we're going to look at are mutation, selection, migration, and genetic drift. The first 3 are pressures. If we know mutation, migration, and selection, if we know numerically what that is, we can predict the outcome. Drift is different. We may or may not get to that today. We'll probably finish up on that on Wednesday. So we're going to look now, first, we're going to talk a little bit about migration. Migration is very simple. As dark-haired Italians move to Sweden because there are blondes there, that's going to alter the allele frequency. That's nothing more than a mathematical equation. There's nothing fancy involved with migration. Having said that, don't be fooled into thinking that migration is something that's very simple and can be overlooked. Because migration actually plays a key role in some things we're going to talk about later in terms of population structure. But the actual analysis of migration is just adding the number of migrants into the new population, subtracting those migrants from the old population, and recalculating P and Q. So that's pretty straightforward. What we're going to do now is take a look at mutation. So mutation is the second mechanism that alters allele frequency. And so these are real pressures. We can determine what direction the population structure will change in. If dark-haired Italians move to Sweden, then the blonde allele frequency will decrease, the dark hair allele frequency will increase. It's just that simple. Mutation is the same way. If we have a very simple population structure, and we have a mutation from the dominant allele to the recessive allele, in the population structure, the allele frequency of big A will go down, the allele frequency of little a will go up. It's just that simple. As the allele frequencies of big A and little a change, with every change, you have to put those numbers back into the binomial to calculate what the population structure is. Remember, population structure is the binomial, p squared plus 2pq plus q squared. The allele frequency is simply p and q. The convention always is that big A is p, little a is q. And so we're always going to do exactly like that. We talked about mutation. Mutation is a natural process. In a population, the mutation never stops. In an individual, the only way the mutation stops is when you die. So this is an ongoing process. You know, one other thing that we briefly discussed should be intuitive. Just as there is mutation from big A to little a, in a natural population, you may also have back mutation. So this is forward. Again, the convention is to always write big A first, and this is back mutation. Notice that I'm writing the forward mutation arrow with a large arrow, and the back mutation rate with a small arrow. That's the convention that tells you that the forward mutation rate is a larger number. In most populations, big A is going to be the predominant allele. Remember I said now predominant. It is dominant, but it is the major allele. Little a is the minor allele, and recessive. Those two need not be connected. If we know the forward mutation rate, we'll call that U, and the back mutation rate we'll call V. So we can measure the mutation rate of big A to little a, and we can measure the mutation rate from little a back to big A. That's the reversion rate. We've done reversions in class. It's not so simple, so I'm not going to give you the derivation of the formula, but what it comes out is Q hat is equal to U over U plus V. What that says is that the equilibrium frequency, this is the equilibrium frequency. If we have a forward and a backward mutation rate, they will come to equilibrium at some point. It's a mathematical formula, but I am not going to derive it for you. As you look at that formula would predict that because the forward mutation rate is the big number and the back mutation rate is the small number, that formula would predict that you would have more little a alleles, that is, more mutant alleles and fewer wild-type normal alleles in a standard population. Everybody understand that? Just looking at U over U plus V, that formula predicts that there will be more mutant alleles, little a alleles in the population. Is that what you see in normal populations? Do normal populations have mostly mutant alleles in them?
No. No.
Why?
Because it's not the wild type.
The math says.
Because it's not the wild type. You see more wild type.
Who cares about the wild type? That's what the formula says. If the answer is no, why is the answer no?
Some mutations are loss of function, so as a result of recessive.
Okay, but that doesn't really answer the question, why are there fewer little a alleles in the population than expected? No, we cannot prevent mutation.
You're not at equilibrium.
The question is then, why is this population not in equilibrium?
That's the homozygous.
No, we're just talking about allele frequency. I have no mention of phenotype.
Is it because there's a lot of recessive mutations, so you need a mutation to be, or to like start the small.
Nope.
Are they selected for it?
How?
Are they selected for it?
Selection. Selection is the answer to the question. Mathematically, you expect more mutant alleles. Why don't you see populations having mostly mutant alleles in the population? The answer is that most, not all mutations, selective disadvantage. Think muscular dystrophy, think cystic fibrosis, think any number of mutant alleles that float around in the population. They are not coming to equilibrium because they are selected against. And so mutation is number 2. We already talked about migration. All these things around it. And so next, so now we can talk about selection. Yes?
My notes, this is Wednesday, right? Or last,
Today's Monday.
yeah. So I don't have anything about migration or, the last thing I had is founder effect at the amount of time.
We just, like I said, we just talked about it briefly. If a bunch of dark-haired Italians go to Sweden, that's, so I didn't develop any formulas, we didn't go into it in any detail, but that's the bottom line. It's just adding numbers. You add the number of migrants to Sweden into the alleles and subtract them from Italy. Louder. I still didn't hear you. Yes, so that, again, so we're going to set up a whole bunch of conventions for using these symbols. P and Q, P is always the dominant, big A, Q is always the recessive, little a. Now, there are certainly gene systems that differ from this. We're not talking about dominant mutations at all. We're talking in the simplest case example possible. That's what we're going to do. Is P is going to be the dominant allele, dominant, not necessarily predominant. Q is going to be the recessive allele, which could be either predominant or not. So the blonde allele is predominant in Sweden, even though it's still recessive. And so what we're investigating is what dictates allele frequency. Why is blonde allele the recessive allele, the predominant allele in Sweden, but not in Italy? That's what this is all about. And so the reason that this never comes to equilibrium, according to the prediction of the formula, is that selection operates against it. Any questions on that? So let's look at selection. Selection is a set of mechanisms that alter reproductive success. Very, very simple formula, a very, very simple definition. It's just a set of mechanisms. We've already talked about selection, actually a number of times. A farmer selects the cows that give the most milk to use as breeding stock for the next generation. That alters the allele frequency. That means because he's selecting those cows that give the most milk, whatever those alleles are that give the most milk are going to increase in allele frequency. The lion selects the slowest zebras to eat and therefore takes those alleles, those slow alleles, out of the population. The lion doesn't realize that's counterproductive because he's selecting for fast zebras. As you eat up all the slow zebras, all that's left in the population are the fast zebras that keep getting faster and faster. The lion needs to find a trick to eat the fast zebras and leave the slow zebras. but he doesn't know that. That's what selection is all about. It's just a set of mechanisms. Whether a farmer does it, or whether a lion does it, or whether the environment does it. As a drought comes, plants that do not have drought-resistant genes and alleles are going to die. Rare plants that have drought-resistant alleles, those alleles will increase in number as those drought-resistant plants will increase in the population. One of the best examples is what happened back in the 50s, when people started spraying DDT on mosquitoes. Before DDT was sprayed on mosquitoes, mosquitoes had a DDT-resistant gene, but that gene was a bad allele. That DDT resistance was bad. Its number was very, very rare. And so spraying DDT killed all the sensitive mosquitoes, and now what had been a poor allele that was selected against normally now became the greatest allele in the world for mosquitoes, not for us. And so DDT resistance spread throughout the world. All selection is a mechanism, whether it's lions eating slow zebras or whether it is DDT spraying on mosquitoes. Does everybody understand that definition? So selection, we're going to let equal S in formulas that we're going to use. The opposite of selection, well, the mirror image, is fitness. Fitness is relative reproductive success. And fitness in the formulas we're going to use is always W. And so the relationship between fitness and selection is 1 minus. Very, very simple relationship. The more, and I should say, selection, of course, can be positive or negative. That is, you can either select against slow zebras or select for fast zebras. Mechanisms are different. There are all kinds of formulas. There are all kinds of variations on the theme. We are only looking at selection against. So that's the first thing you need to know. We are only going to select against, and we are only going to select against the recessive allele. Again, as you change the parameters, as you change what you're doing in these formulas, the formula also changes. So we're going to look at one very restricted type of an example of selection against the population. So we only select against the recessive for the formula that I am giving you. But anybody have a question on that? Yes?
Wait, wouldn't it be like a W equals 1 minus S, or?
That's right. So look it around.
Right.
That's the way we're doing it. Yep. Anybody else? Any questions before we do a problem? So we're going to start out with the population. So we have a population that 50% of the population has the dominant phenotype. 50% of the population has the recessive phenotype. Like I said, we are going to do selection only against the recessive allele. So in order to do that, we need to break this population down so that we can figure out big A, big A, big A, little a, little a, little a. We already know little a, little a, because we can see it. We cannot see the other two genotypes. We can only see the phenotype. And so we're looking at a dominant phenotype, and we know the genotype of the recessive phenotype. But we have to be able to calculate and divide up this 50% into the two different genotypes. Only way, and I'll give you a hint on how to do it, only way we can do that is if we assume the population is in Hardy-Weinberg equilibrium. So how would you divide up the 50% of the individuals that are in the dominant phenotype? How would you divide them into homozygous class and heterozygous class? Say that again? Okay, kind of. You're about halfway there. But there's just one little bad assumption in what you said. But you've got the right idea. Generally. How is it possible to divide up that dominant phenotype class into the two genotypes?
If you assume it's in Hardy-Weinberg, you set it equal so that you find your 2PQ. You set it equal so you find your 2PQ and then go backwards from that to show that you're equal heterozygous, and then just whatever's left over is your...
How are you going to get 2PQ?
Well, you know
You don't have
Q,
P or Q.
P plus Q equals what?
By my relay is Q squared. So
So the only way that you can do this is because I said that the population is in Hardy-Weinberg equilibrium. And so you know that this has to be P squared 2PQ, and that has to be Q squared. Only way we can do it is because it is in Hardy-Weinberg equilibrium. So now, assuming that, we can let Q squared equal 0.5. And that means the square root of Q squared will give us Q. That's the bad news. You've got to be able to do this on the exam without a calculator. So I confess, I'm so old, I can no longer do square roots on paper. When I was in high school, I could do it, but it's gone. But old people have a really good way of doing really fast math, because I didn't grow up with calculators. So the way I do it, I would take 0.2 times 0.2 is 0.04. No, 0.3 times 0.3 is No. 0.5 times 0.5 is 0.49. Ooh, that's close enough for me.
Budget 5.
0.7?
Yeah.
So that's an approximation calculation. I was so anxious I left off 5 and 6. But you know what they are. That's how you do it. I'm serious. There's no other way. So I promise I will give easy numbers on the final exam. But you have to be able to do simple math. So that means Q equals 0.7. So if Q is equal to 0.7, that means P is equal to 0.3. So P squared is 0.09. 7 times 3 is 21. 42. That is the population structure. Now that we're past the square root, does anybody have a question on how I solved and did the population structure, assuming that it's in Hardy-Weinberg? That's the only way. There's no other way to do it. So the whole point of this is because I'm going to select against this population. I'm going to make this population W equals 0. Now remember, there are all kinds of different formulas. The only formula that we are using is a formula where we are selecting against the recessive gene. And so that formula is Q equals SP Q squared over 1 minus SQ squared. Right. That's that delta Q. That's the change in Q. So that's a formula that you've got to memorize. This problem will be on the final exam. So remember, the mini-final is only about a week and a half to 2 weeks worth of material from the end of developmental biology. And so now it becomes very, very simple. So we're going to ask the question, what happens to this population if the fitness of these homozygous recessives becomes 0? Fill it in. What's S? What? Yeah, but what's the value? 1. Okay. What's P? And Q squared 0.7 divided by 1 there. I set this up deliberately. Huh? Q squared is 0.5. That's Q squared. Listen, I did this deliberately. There's Q squared, and there's Q squared. It doesn't matter. 0.7 squared or 0.5. Now we'll cut to the number. No, 0.3. So this says that if somehow this is a mosquito population and we strain it with DDT such that the recessive has 0 fitness we are going to alter the allele frequency of little a is going to go down 0.3. So new A is equal to old A minus 0.3. Old A was Q. Everybody follow? So 0.7 minus 0.3 equals 0.4. So that makes new P equals P of 0.3 plus 0.3 equals 0.6. So new Q, new P. That's just simple math. You can calculate now the population, P squared plus 2PQ plus Q squared is 0.6 squared plus 2 times 0.6, 0.3 plus 0.4 squared. And what you'll see, I think I have it down here someplace. No, I guess I don't. It's easy to calculate. What you see is a huge alteration in the population structure by absolute selection. Zero fitness on that little a allele. That's virtually what happened to mosquitoes. Notice that little a doesn't disappear. It's not even close to disappearing. But it really went down a huge amount from 70% to 40%. Is little a ever going to disappear? Why not? Why won't little a disappear completely if we keep having zero fitness? Back mutation is one answer. Back mutation from big A to little a, you're never going to stop mutation. There's old Q and new Q. So old Q is just here. Oh, you mean the number Q? Yeah. Oh, you mean that, because it's the same.
No,
In the new population, number A, use 0.3 and 0.4 Q. Oh, then I just made a mistake. Where am I?
it's supposed to be 0.4 times 0.6 times P.
For P?
Yeah. No. It's 0.6 times 0.4 plus 0.4 squared.
Okay, sorry. Yeah, sure, it's right there.
Heterozygous while carrying a little bit.
And that's the other reason. So even if we did this over and over again, and I think your book has a formula that allows you to do this and say, okay, what happens after 3 generations? We're only doing a formula that allows you to do 1 generation. So the answer to the question, why doesn't little a allele disappear when fitness is 0, is first of all, you have a whole bunch of little a alleles hidden in the heterozygotes that is absolutely unaffected by this selection. And the second reason is that recurrent mutation from big A to little a will always keep a small amount of little a allele in the population. That's why muscular dystrophy doesn't disappear. That's why hemophilia, all the genetic diseases, they've been with mankind for centuries, millennia. They will not go away because of mutation or because of heterozygotes. Yes?
How did you get a negative number for 0.3?
Because we're selecting against. I made it negative. So the assumption is, and that's a good question, the assumption is we're selecting against, which means that it will go down, Q will decrease. And so I could have put it in up here, but I didn't. Yes?
Would we have to change our S value if we're selecting for the mutation? Or would it still just be 1 because of the
Well,
equation?
selection is selection, but again, we're only doing selection against. So there's a whole other world of formulas and assumptions selecting for. Any last questions on the formula, how to use it, and what's going on? Yes?
I guess it's more like, how do you find the P exactly?
It's the correct note. So once we have Q, you can do it either from new Q, add that number down. We'll see you on Wednesday.